A closer look. A closer look will come after Lesson 1, but before Lesson 2. Before we look at examples 1 and 2, let's take a look at some general functions. Each of these functions is a particular function. You may recall the term particular function from differential equations. A general function had, let's say, f of x equals cosine of x plus c with a constant of integration. But particular functions have the constant of integration already established. That's the case here for f of x equals cosine of x plus 3, g of x equals x to the 5th plus 1, and h of x equals x squared. Inherent to h of x is a plus 0. And inherent to each of these functions are a whole host of conditions. For instance, we may say f of 0 is equal to 4. We didn't have to be given this condition. We could find the condition. For another example, f at pi would simply be 2. G of 0 is 1. G of 2 is 33. H of 0 is 0, and h of 2 is 4. In example 1, we're asked to find a power series for the natural log of 1 plus x, centered at x equals 0. Now, we've done this example before, but we're going to look at it a little bit more carefully with some new terminology. We'll start by saying that the natural log of 1 plus x is the antiderivative of 1 over 1 plus, now I'm going to use a dummy variable t here, dt. Now, this tells us it's centered at 0, so I need 0 in the lower bound. That's new as compared to when we talked about this before. And then x goes up here. Before, when we talked about it, I just put a 0 and didn't explain that it was because it's centered at 0. Okay, so the next thing we're going to do is write the 1 over 1 plus t as a power series. So that's going to be a geometric power series, 1 minus t plus t squared minus t to the 3rd plus dot 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 dt. And then I'm going to integrate here term by term by term. So the integral of 1 is t. Then we have t squared over 2 plus t to the 3rd over 3 minus t to the 4th over 4 plus dot dot dot. And then we need to take that from 0 to x, employing the fundamental theorem of calculus part 2. I'm going to first plug in the x, which is going to give me x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot dot dot. But then I also have to subtract the expression when I plug in 0. And that's just going to be a whole bunch of zeros. So essentially I am subtracting 0. So this 0 then can be thought of as a condition of the natural log of 1 plus x when it is centered at 0, which the condition can be figured out, doesn't have to be given. And f of 0 is going to be the natural log of 1, which is 0. So this 0 here is a reflection of centered at 0. And if it's centered at 0, it gives us a corresponding condition, which then shows up here kind of like a constant of integration. Now I'm going to just write it without the 0. So x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot dot dot. And I would like to summarize this with some summation notation. We'll go from 0 to infinity, negative 1 to the n. It strictly alternates. X to the n plus 1 all over n plus 1. Or we could have written this indexed at 1. So we'll go from 1 to infinity, and then it's going to be negative 1 to the n minus 1, x to the n over n. Perhaps that looks a little bit more clean. Now I've written a power series for the natural log of 1 plus x centered at 0, but it's not complete until I give the interval of convergence. If you recall, when I take the integral of a power series, I may gain points of convergence. If I take a derivative, I can't gain, I could possibly lose points of convergence. So let's talk about the interval of convergence for this series. For the geometric series here, the interval of convergence is clearly -1 to 1, not including the endpoints. But see, we integrated this series, so we may gain points of convergence on the interval. Namely, we may gain the -1 or possibly the +1. So we need to test the endpoints. So if I let x equals -1, I'm going to plug the -1 in for x to my power series, and then I have this here. So what does this become? Well, it looks like this is always negative, so I'm going to pull out a negative, and then I'm left with the integral from, the sum from 0 to infinity of -1 to the 2n over n plus 1. And that becomes negative the sum from 0 to infinity. Well, -1 to the 2n will always be positive, so simply 1 over n plus 1. Now, you should recognize this. This here is the harmonic series which diverges, and then if it's simply negative, it's just going to diverge in the negative direction. So this diverges as the harmonic. It's not the alternating harmonic, it is the negative of the harmonic. And then we look at the next endpoint, x equals 1. And this time when I plug x equals 1 into the power series, we have the alternating harmonic. So this converges as the alternating harmonic. So now we have the complete interval of convergence. The -1 is not included, and the +1 then becomes included. So this is the interval of convergence for the power series, which, let me scroll up, for the power series for the natural log of x plus 1 or 1 plus x centered at 0. Let's take a look at example 2, and you're going to see some similarities and differences. This time they want a power series for f of x, but they give us f prime of x. They say that f prime of x is 1 over 1 plus x. This is the domain, and they want us to write a power series centered at 0. What makes this problem different is we do not have the particular function, so we need a condition. Without a condition, we would not be able to find the power series they're asking us for. So in this case, they give us a condition at 0, and that makes sense to give us a condition at 0 because it's centered at 0. And the condition is that f of 0 equals 5. So now we begin, and we say that f of x is equal to the antiderivative of f prime of x dx. And so that's going to be the indefinite integral of 1 over 1 plus x dx. See, I don't need a dummy variable here because I do not have defined bounds. And so, like we did in the last part, we're going to write a power series for 1 over 1 plus x, this time in terms of x. 1 minus x plus x squared minus x cubed plus ... dx. That's a similarity. And so this is going to come out to be x minus x squared over 2 plus x to the power of 3 over 3 minus x to the power of 4 over 4 plus ... Now here's where it differs, because we need a constant of integration. With the indefinite integral, we always need a plus c for constant of integration. So we have to use our condition in order to find what the value of c is. And I'll say f of 0 is equal to, we're going to have a whole bunch of zeros here, and then we have a plus c, and that equals 5. So therefore, my c must equal 5. And then my power series becomes f of x equals, I'm going to put my plus c up front, so 5 plus x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus dot dot dot. And if I was summarizing using summation notation, I would say 5 plus the sum from 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. So hopefully this closer look gave you some insight into how the center gets incorporated into these power series and how it reflects in the bounds of the integrals.